Are you ready for some more punishment? Well, you must be, because you wouldn't be watching this video if you weren't. So here we've got another structure, and this structure is another ether, because I see the ether functional group. And we need to determine how many NMR signals come from the following compound. Okay, so we need to go through and we need to figure out how many different types of hydrogen actually is present in this compound or this molecular structure. So very first off kind of thing, I already see this carbon with the 3 hydrogens over on the right, and that's quite different than any of those that are nestled together over here to the left. So that means that we're probably going to find, ding ding, a signal that is going to come from those 3 protons, and those 3 protons are all equivalent to each other, so that signal would be in reference to those 3 protons in that structure. Now, to the left of the oxygen, this is a little different, and the reason is because these hydrogens are on a carbon that's directly connected to the O. And these hydrogens, they're not that way. These hydrogens are on a carbon that's connected to another carbon before it's connected to the O. So that means that these 3, sure enough, they're going to be different. They're going to see a different type of signal than the hydrogens to the right-hand side. So I already know the one on the right-hand side, it's different, it's connected differently, there's 3 of them, they're all equivalent, I get 1 signal from that side. Now I need to question this left-hand side. I need to see, are these going to be equivalent hydrogens, yes or no? And the answer to this is, if you do not know, then you know what I'm going to do. You're going to take one of these hydrogens and you're going to and you're going to replace it with something like a bromine, and you're going to name it, or at least try to name it. Would you get a different name if bromine was here on the top carbon, or if bromine was there on the left-handed carbon, or if bromine was here at the bottom carbon? Would you get different names based on that position? And the answer that you will find out is no, you will not get a different name. So these 3 carbons are all identical carbons to each other, which means that ding, 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 we're going to get a signal because they're different than the one to the right-hand side, which we've already said. That's going to be our first one. So this one is going to be different. However, the signal that we get from these 3 hydrogens will be the same signal as those 3 hydrogens, and it will be the same signal as these 3 hydrogens. So we're going to get a second signal here. There's 2 signals in this molecule, but this particular signal will represent 3, 4, 5, 6, and 7, 8, 9 protons, because those 9 protons are all identical to each other. They're in the same spot. They are attached the same way. They are equivalent. Therefore, they give us an equivalent signal versus the one on the right-hand side. So 2 signals, 1 representing 3 protons, 1 representing 9 protons. All right, let's keep going. We're on a roll. You're probably feeling really good about what you're doing right now, and at least I hope you do. So let's do a CH3, and then an oxygen, and then a CH, and then a Cl2. How many signals would you get? That's the game. All right. So we're going to look at this, and we're going to kind of not do baby steps anymore. And I'm going to see, oh, okay, so hydrogen NMR is what they're referring to. I need to look at different hydrogens. Well, these are 2 chlorines. There's nothing there. That doesn't make any sense. Why would you circle that for an answer? If you circle that for an answer on a test or an assignment, I swear I should just automatically give you an F for the entire semester, because this is hydrogen NMR and you need hydrogen to do hydrogen NMR. All right, so that's Cl2, nothing from there. This is a hydrogen that's attached to a carbon. Ching-ching! There we go. We're going to get a signal. Now the question is, are there different hydrogens to give me different signals? I mean, the presence of a hydrogen is going to make this thing give me a signal in H and MR. So I look at the oxygen to the right-hand side, that is a carbon with 1 hydrogen. To the left-hand side, it is a carbon with 3 hydrogens. So therefore, cha-ching, I already know. One side has 3 on a carbon, one side has 1 on a carbon, so therefore they are different. They are not equivalent here. So I'm going to get 2 signals. One of those signals represents 1 hydrogen, and the other signal will represent those 3 hydrogens, right? So again, folks, this does not have to be complicated. It's just a matter of you understanding molecular structure. That is what this is all about. So think about the days of infrared. Think about the days of mass spectroscopy. All of these were all about molecular structure. That's what it was. And we're doing the same thing here, just with a different instrument giving us different spectra. It's not IR spectra. It's not MS spectra. It is NMR spectra. Okay? So here we get a molecule, and oh my goodness. Oh my goodness. What we see here is a double bond. Oh, I remember that from Orgo 1. Orgo 1 told me that was called an alkene. All right, so we have an alkene structure. And that double bond's pretty important. We're going to have to pay attention to it because remember, all this time I have often said, you need to take a look at hydrogens, you need to the hydrogen, and you need to replace it with something like a bromine. Then name it. Do you get something different? Yes or no? So what this means is that I need to take a look at the different types of hydrogens that are present, and I need to figure out, am I going to get a different signal, yes or no? All right, well, first off, I can already tell you, this carbon that has 2 hydrogens on it, that is different than these 3 hydrogens over here. These hydrogens are attached to a carbon with a double bond. These hydrogens are attached to a carbon without a double bond. You got to go the next carbon in order to get that. So those are different. They're different right off the bat. So I know that I'm going to get a signal ching, ding, over here to the right-hand side. Now the question is, do we get a different type of signal to the left-hand side? And the answer is yes. I just answered that. Yes, we're going to get a different signal to the left. So this is a CH3 group, and this is a CH3 group, and these 2 CH3 groups are the same. And the reason is because these are hydrogens on a carbon with a double bond, and these are hydrogens on a carbon with a double bond. It is the same group that is coming off of that carbon. So this is the same methyl group as this one here at the bottom. So ding, 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 I'm going to get a signal, and this signal is going to represent these 3 hydrogens as well as those 3 hydrogens. It takes into account both of those methyl groups because they are identical. If you replaced one of those hydrogens with a bromine and named it, you would get the same name as if you did it to the top or if you did it to the bottom. It doesn't matter. The same thing is happening over on the right-hand side. On the right-hand side, this hydrogen is equivalent to that hydrogen. They are both onto the same carbon, and because of that, I'm going to get the same signal. So this signal is going to be in reference to both of these hydrogens that are present on the molecule. So I'm going to get 2 signals here, and I'm going to be careful because it's all about naming, right? And when we talked about the world of naming in alkenes, we said, hold up, we can do a cis-trans or EZ depending on what we have. And EZ is not going to be easy with double bonds in the world of NMR because it's going to complicate our stories a little bit more. And the reason is because it's all about the orientation. If it's a different name, even if it's a different name with orientation, it is not equivalent. If I have a trans double bond, that is different than a cis double bond, and the only difference is the way the atoms are connected to each other. That is it. That's the only difference here. Good news for us. This carbon had a double bond, and on the other side of that carbon, we have a hydrogen up on top and a hydrogen down below. They're the same groups. So therefore, cis and trans cannot be used. It's the same group that's attached to those carbons. They've got to be different. That's the only way that this is going to work. So, just because we're lucky, we get this example problem first, and we don't have to worry about cis and trans, or E and Z. And that's because it's two of the same group on the same carbon. Actually, it's two of the same group on the left-hand carbon too. I mean, a methyl to the top, a methyl to the bottom. These two are identical groups attached to the same carbon. That violates the rules for cis and trans and E and Z. They have to be different. So what if we had an example where they were different? Carbon, double bond, carbon, and I get those prongs that stick out to the left and to the right. Let's put a hydrogen here. Let's put a Br group here. Let's put a hydrogen here. And then let's put a hydrogen here first. How many different types of signals do we get from the NMR? Oh, goodness gracious. I'm going to have to deal with this question over and over and over for video after video after video. Okay. So visually looking at it, this hydrogen's attached to a carbon that also has a bromine. Ding, ding! We get a signal. That is automatically different than the signal to the left. And that's because these hydrogens are attached to a carbon that's not attached to a bromine. They are different position-wise. They are different. So ding, ding! I'm going to get a signal there. And that particular signal takes care of that hydrogen as well as that hydrogen. Both of them. They are equivalent to each other. So two signals from the NMR. No worry about cis, no worry about trans, and the reason is because this carbon to the left-hand side, well, this one has two hydrogens that are together, right? That's just what we said. But it's more than that. This is where the trick begins with double bonds. Because, what if? You remember that? I do that for a reason, and that's for you to remember to do it. What if I erased one of these hydrogens and replaced it with something like a bromine? That's what we've always done. And I've always told you, it doesn't matter what you put there. Most of the time people stick with bromines because it's a halogen and it's the easiest one. How would you name it? Well, you would look at this and you would say, well, there's a 2-carbon chain here. We would call this ethene because it's a 2-carbon double bond. And then it looks like there is a bromo group on one carbon and a bromo group on the other carbon. So it looks like it's a 1,2-dibromoethene. But if I really wanted to be particular, look, you've got to be careful. And that's because by substituting that hydrogen with the bromine, we can generate a name here that's a little bit more specific. And these hydrogens are across from each other. And back in the day in Orgo 1, if hydrogens are across from each other like this, then that means that this is a trans 1,2-dibromoethene. That would be the name if we did that substitution, right? So now I'm going to go back and I'm going to put the hydrogen back at that spot. And then we're going to do the other hydrogen. We're going to here, and we're going to put a bromine there. And now I'm going to ask you to do it again. I'm going to say, if this was the structure, what would be the name of it? So you would look at that and you would say, well, I still have the ethene. Still there. That doesn't change. I also still have a 1-bromo and a 2-bromo group. It's still a 1,2-dibromo there. That's not changed. But, what has changed is the stereochemistry of the double bond. Because you could be more specific here, and these hydrogens are on the same side. And because those hydrogens are on the same side now, this would be the cis form of that molecule. So you've got to be careful. And that is why I tell you, until you really get it down, until you are 100% sure of NMR signals, always sit down with the structures, erase a hydrogen, put a halogen on it like a bromine, and see if you get different names. Because in the beginning, I somewhat misled you. And I made you think that the two hydrogens over on the left-hand side were identical, and they are not identical. They are hydrogens. They are both connected to a carbon. But you see that if we substitute one with a halogen and name it, we get a different name depending on what we do with it. Because stereochemistry causes us problems in NMR. I hate stereochemistry. And I still hate stereochemistry because it even weasels itself into the NMR theory to give us answers like this. So, the true answer to this problem, folks, you've got 3 different hydrogens here. And because you have 3 different hydrogens, you're going to get 3 different signals. Do not let these types of compounds trick you, because almost they will do it every single time if you're not careful. And I don't want you to be one of those people. I want you to be better than everybody else. And I want you to be able to take a look at compounds like this and catch the tricks. Catch those tricks where it looks like they're identical and they are not. So now we see whenever double bonds show up, double bonds are going to cause us a problem. We're going to have to slow down, and we're going to have to take a closer look at these molecules when they begin to form and produce the NMR signals. So we really do get 3 signals here, and it's all due to that silly little double bond. All right, now let's take a look at something like benzene. All right, so double, single, double, and then off of each one of these, we are going to get a hydrogen. How many NMR signals do we have? Compared to all the others, this is going to be easy. All right, so if I that hydrogen and put a bromine on it, no matter where I the hydrogen, I'm going to get the same name. Whether I do it to the top, or whether I do it to the bottom, or whether I do it to the left, or to the right, or to the top right, or to the top left, it doesn't really matter. It's the same hydrogen all the way around. So this hydrogen is equivalent to all the others, so therefore I get 1 signal from the NMR. That is it. They're all equivalent to each other. Nothing else on the benzene. There is no O and M's and P's. No, there's not. There's no groups on there to be O and M and P of each other. They're all hydrogens. You can't have OMPs. However, but if I give you an example that has a group on here already, and then I say, how many signals does this molecule have? It is not 1. Because now we really are OMP in it, folks. So if I look at the nitro group that is already on there, that nitro group is attached to a carbon, and that carbon has no other hydrogens. No more. So we get the carbons to the left and to the right. This is ortho, and that's also ortho. So if I that hydrogen and put a bromine there, that bromo group and the nitro group would be ortho to each other. That is the same as if I did it to the right-hand side here. There's no other groups on there that I need to pay attention to, right? So, ding, 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 ding. I'm going to get a signal here, and that is the same as if I did it to the right-hand side. So there's one signal that represents those two hydrogens. Right? Then I go on. This would be the meta position of the benzene ring. If I the hydrogen there and put a bromine there, that would be a bromo nitro, and that's a meta position. That would be the same as if I did it to the right-hand side. So those are identical. So ding, 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 I get another signal. There's a second signal from that structure. And then finally, if I did the directly across the NO2 group, that is the para position, right? Again, all of those things coming back. That's the only para position that we have. So therefore, that hydrogen will be different because it's the only para versus the two metas versus the two orthos. And folks, what that means is that this structure will have 3 signals in total that I will have to worry about. So not only do double bonds cause us problems, I'm going to put a big exclamation mark here, but you're also going to have to look out for benzene rings as well. Because those benzene rings, depending on what they are, depending on what is there, could, in fact, give you 3 different signals. Possibly 3 different signals. Just due to the ring being present. All right? Okay, so we've done some example problems there. And folks, we can continue on. And that's what we're going to do in the next video. I'm not going to take it for granted. If you feel like you're okay with this, then blaze through the next video. I don't care. However, you're going to see more and more complicated examples possibly that will be presented in the next video. And even if you feel good, I would still encourage you to watch the next video. And the reason is because practice makes perfect, or at least close to perfect. And that's what we want on these NMR structures. So we're going to take a look at these structures. We're not going to anything out, and we're just going to look at them and quickly identify whether or not, in fact, we have an appropriate number of signals from the NMR spectrum. So come back, take a look. Our example problems will go letter A through O. That's how many we'll do in the next video. So practice, practice, practice.